everyone. Thank you for the introduction. My name is Behkish Nassirzadeh, and I am a PhD candidate at the University of Waterloo, the very first university that Ethereum was created in. And fun fact, when Vitalik was doing his undergrad, I was actually doing my undergrad at Waterloo as well. I'm excited today to talk about our latest project. It's called Gas Gauge, and we basically fully automatically detect and repair gas vulnerabilities in Ethereum smart contracts. This work has been done by my PhD supervisors, Professor Anwar Hassan, Professor Vijay Ganesh, as well as my colleagues, Jolly Sun and Sebastian Benescu. Here's a table of content of what I'm going to talk about. I'll give a very brief introduction of gas mechanism on Ethereum. Then I'll jump in the problem that we're trying to solve. And our solution has two parts, the detection part and the repair part. So many of you may have already heard or know about gas. Gas basically is a measurement unit in Ethereum smart contracts. This is basically the amount of computation that's required for a transaction to be included in a block. And in terms of limits, gas has two limits. The first limit is the transaction gas limit, which is set by the transaction initiator, the person that tries to call the transaction. And this is basically the amount of gas or money they're willing to pay for their transaction to be included in a block. The second limit is the block gas limit, which is set by the network and the miners or validators. And this is basically the maximum amount of work a miner or validator is willing to do to form a block. So that means by nature, because one transaction has to be included in at most one block, any limit that applies to a block automatically applies to the transaction as well. So that means the maximum amount of limit that you can put for a transaction gas limit is block gas limit. So it's important to choose a transaction gas limit properly. And that's because the caller has to pay the gas fees upfront. So if the transaction gas limit that the caller sets is greater than or equal to the actual gas needed for a transaction, then the transaction goes through, it gets included in a block, and remaining gas will be paid back to the caller. However, if the caller sets a lower transaction gas limit than the actual limit required to perform that specific transaction, then the miners start doing the work, then they run out of gas, and because operations and transactions in Ethereum are atomic, it means that either all the operations have to happen or none of them have to happen. And that means once it goes out of gas, all the operations up until that point will be reverted back, and as a result, there will be no state change. So in other ways, you pay for the gas fees, nothing happens. And that's why we call this a gas wastage. With this mechanism, it comes a lot of benefits, but it also introduces a few vulnerabilities. And these vulnerabilities are typically known as gas-based vulnerabilities. And in fact, they are one of the top 5 most common vulnerabilities in Ethereum smart contracts. So what it is, in simple words, is that when you have a function in a smart contract that by default, by nature, requires more gas than the block gas limit. So that means no matter how high you set the transaction gas limit, because it actually requires more gas than the block gas limit, it will always result into an out-of-gas error. And it's an interesting case because it could include an attacker that tries to damage the reputation of a smart contract, and it can result in funds being locked in the smart contract. Or it could be just a poor coding pattern that it results into gas wastage of the users using that smart contract. We've performed multiple analysis, and we resulted that over 90% of the smart contracts that are vulnerable to these specific vulnerabilities have at least one loop that their bound is controlled by input variables. Let me give you an example so we can understand what exactly I'm talking about here. So here we have a very simple smart contract. Let's say this is a small bank smart contract. and it has one very simple function. And that function is to add interest to the users of this bank. So the users are stored in a fixed array. And let's say at the end of each month, the owner of the bank calls the function add interest. And there is a loop that traverses through the entries of that array. And based on that, all the users of that bank get some funds. So here the issue is each iteration of that loop consumes a certain amount of gas. And the more iterations we perform, the more gas we're going to consume. And that means if we ever run out of gas at any point in this loop, all the operations up until that point will be reverted back. So let's say we perform the first 999 users, we add interest to them, and then we run out of gas. What happens is that all that 999 operations will be reverted back, and no one gets their money. However, the first example has a very low risk, and that's because the behavior is pretty much predictable. It's a fixed array, and we can generally predict the amount of gas required to call this function. And if there are any issues, it will be detected during testing. But then we have another case that might be a little bit more problematic. So for example, in the second function that I'm showing here, it's basically the same functionality, but instead of having a fixed array, we have a dynamic array that's a user input. So this input variable basically controls the number of iterations in this specific loop. So that means if the user has an array that has, let's say, 2,000 entries, then it's going to cause an out of gas, and the user has to pay for the gas fees. And then they have to choose a smaller array, and then if it goes through, then that's good. If not, then they still have to pay for the gas. So this case has a medium risk because it results into gas wastage. But at the same time, there are ways to avoid it by using a smaller size array as our input. The most problematic case is the case that a state variable is the one that affects the number of iterations in a loop. So for example, here in the first function add user, we take the address of a user and add it to our dynamic array. And then later on, when we call the function add interest, we traverse through the entries of that array. However, as you can see, the issue here is that there is no functionality to remove any elements from that array. That means once we reach the maximum iterations of that loop, and then we add more entries to that array, it's game over. No one can get their money. There is no functionality to reduce elements in the array. So no matter how high you set the transaction gas limit, this will always result in an out-of-gas instance. So as a result, the funds in this contract will be locked, and no users can get their money. So in 2019, QuantStam, which is one of the biggest auditing firms for Ethereum smart contracts, came to us, and they were wondering if we can implement a tool to detect and repair this type of vulnerabilities automatically. And the reason is this kind of vulnerabilities are fairly easy to detect, but the process of repair is very time and resource consuming. In fact, just to find the maximum number of iteration of a loop, it takes about 4 hours per loop, and 1 or 2 engineers have to work on that. So these are the 10 steps that you normally have to take to fix such a problem. I'm going to show the example and go through the steps together so we can see how tedious the work is. So let's work on the first 2 examples that I showed earlier. The first step is that we have to detect the problem. So in this case, we have loops, and we can quickly detect them using something like a static analysis or just by reading the code. The next, we need to find the variables that affect the loop and the type of those variables. So for example, in the first example is a constant variable, and the second example is an input variable. And then we need to perform something called gas analysis. So basically, this is the amount of gas that's required to perform each of the iterations of that loop. And then based on the current gas limit, we can estimate the maximum amount of iterations that a specific loop can perform before running out of gas. So I believe the current block gas limit for Ethereum is 36 million gas. And that specific operation inside the loop consumes about 20,000 gas. So we can safely perform about 1,800 iterations in the loop before running out of gas and before it becomes problematic. So that means for the first example that we have, the risk is fairly low because we only have 1,000 entries. However, for the second example, if the user's array has more than 1,800 entries, so let's say 2,000 addresses, then it will result in an out-of-gas instance, and as a result, the user will lose some gas. Then the next step is to perform a risk analysis, as we saw in the previous slides. So the risk for the first case is pretty low. The risk for the second case is medium. Next step is to derive the gas usage formula. So basically, based on the gas analysis that we have to come up with a formula that then we can insert it into a require statement right before the loop to avoid gas wastage. So how it works is that that require statement gets executed before the loop is executed, and it checks to see if you have enough gas to perform as many iterations as we need in the loop. If we do have that, then that's safe. We can enter the loop. If we don't have it, it terminates the program right away, and it basically stops the user from losing gas. Step 8 and 9 or 10 are for the case that a state variable controls the loop. We don't have that in these two examples, so we can skip it. But now let's look at the case that we do have a state variable controlling that loop. The first 7 steps are more or less similar to what we've seen before, but step 8, 9, and 10 are different. In step 8, we have to analyze the contract and the loop and find the state variables that affect the loop and find the functions that write to that state variable. Then we need to see how likely it is for that state variable to reach the maximum limit. So for example, in this specific instance, it's 1,800 users. It's pretty probable, so it's very risky. And as a result, because there is no functionality to reduce the number of elements in the array, we need to repair this contract, and we need to add the functionality ourselves. So as a result, the modification of the contract would be something similar to this. And obviously, there is no recipe that fits all. So there is multiple patterns that we have to consider, the code logic, and so on. And so if you're wondering how things are done in practice right now without any tools, basically, the developers developed a smart contract. They pass that to auditors to check for logic flaws and security flaws. If the auditors find any security flaws, for example, denial of service with block gas limit, then they perform the gas analysis to the developers, and the developers have to try to fix and repair the program. Then they pass it back again to the auditors, and they go back and forth until both parties are happy. And in terms of time that it takes about 2 to 3 days for the auditors to audit the smart contract, and it typically takes about a few days to a couple of weeks for the entire process to be done. And that's basically the motivation behind the toolchain that we designed. So in 2020, we started thinking about an automatic system to detect and sort of repair this specific vulnerability. And as a result, we developed GasGauge. GasGauge is able to detect all these vulnerabilities automatically, and it provides the gas analysis so the developers can repair the contract manually. And it basically saves a lot of time from the auditor perspective. We were trying to find a repair at a time to automatically also repair the contracts. But because the patterns are different and the codes can be complex, we weren't able to find any automatic tool up until 2023 with the LLMs becoming a big thing. And we started thinking, can we use LLMs not to detect, because they're not that sufficient at detecting, but to repair, because they're pretty decent at writing code, and they also support Solidity. And GasGuard was the first tool that we designed, and GasGuard is able to generate that require statement that I talked about earlier. And our recent project, GasGauge, completes the toolchain by fully repair the smart contract that's vulnerable to DOS with block gas limit. OK, so let me briefly go over how gas gauge works. So gas gauge is a static dynamic analysis tool. It takes the smart contract, it runs some static analysis to see if there are any loops that might be problematic. If it finds anything, then it passes the results to a fuzzer, and the fuzzer tries to generate test cases and fuzzes the contract to find an instance of out of gas. The beauty about fuzzers is that if they find something, that means it's 100% correct. So there is no false positives. However, because the quality of fuzzers depend on the quality of the test cases that you write for them, there might be a lot of false negatives because their search space is pretty huge. By using a static analysis, we can reduce that search space so we can increase the accuracy of the fuzzer. And the last step is that we pass the result to a dynamic analysis, is a runtime verifier that tries to find the amount of gas used per iteration, and then based on that, the amount of the maximum iterations the loop can safely perform. And it generates a report like this that it basically has the gas analysis, has all the information a developer needs to fix the smart contract. And in fact, it took only 15 minutes on average per loop for gas gauge to automatically generate that report. That before gas gauge, it used to take 4 hours for auditors to manually perform that. And the accuracy of gas gauge on the 1,000 real-world smart contract that we tested it on was 99.7%. So that brings us to the era of LLMs. In 2023, we started thinking about incorporating LLMs to get the result from gas gauge because it's super accurate to detect the vulnerabilities, and it does provide very useful information to fix it. And we wanted to see if we can pass that to an LLM to generate the repair automatically as well. So GasGuard is our first attempt to automate the process of repair. The way it works is that it takes the output of gas gauge, it passes it to another static analysis tool, and this static analyzer tries to summarize the contract, the loop, and the variables affecting that loop, because the input tokens that you provide to the LLMs are very limited, and sometimes you cannot input the entire contract to LLM. So we wanted to just summarize and provide the information needed for the LLM to provide the fix. Next, the report will be fed into our LLM, which is fine-tuned on over 350 examples. And the LLM tries to provide that required statement automatically. So as a result, for the given input, the output would be a contract that has that GasGuard right before entering the loop. At the time we were working with LLMs, GPT 3.5 was the strongest GPT that was out there that we could fine-tune. And we tried to do a fully automated repair of a smart contract, especially for the case with state variables. But at the time, GPTs weren't as capable of writing complex code. So we took one step further, and we wanted to see if we can use a similar approach to another vulnerability that's a little bit simpler than gas-based vulnerabilities, but we wanted to see if LLM is capable of fully detect and repair the contracts. And as a result, we chose integer overflow and underflow vulnerabilities, and we just modified our design a little bit, mainly in terms of our data set, and we were able to get an accuracy of 95%. So the LLM in this case was able to completely and automatically fix the smart contracts. I know this specific vulnerability is automatically being detected in Solidity version 8 and higher, but we chose this vulnerability because it was pretty easy to train our LLM with, and it was easy to get access to contracts that are vulnerable to this vulnerability. We basically just wanted to see if there is any hopes that we can use LLMs to fully automate the process of gas-based vulnerabilities. So that brings us to our final tool, GasGauge AI. We started developing GasGauge AI from last year. And this is a fully automated 3-layer LLM-based repair program. This one takes the output of GasGauge, again, passes it to another static analyzer the static analyzer finds the state variables that affect the loop, and then finds the functions that write to those state variables. And then it passes it to the first LLM, where the first LLM writes test cases for our fuzzer. In this case, we chose Foundry because it's super fast, super efficient. And so the first LLM's task is to write test cases that test to see whether there is a function that can reduce the number of iterations in that loop. If the functionality exists, the fuzzer is able to find it. The fuzzer has 0 false positives. So if it finds it, for sure the functionality is there, then we can get out of the repair process because the contract is already repaired. If the functionality is not there, then we pass the result to our second LLM, which is fine-tuned on about 50 examples. We use GPT 4.0 for this one. And this one tries to repair the contract. So if the functionality to reduce the iterations in that loop is not there, then LLM2 actually writes Solidity code and tries to find that, tries to fix that contract. Once LLM2 is done, the result is passed to LLM3, which is our feedback engine. And the job of LLM3 is to see whether LLM2 did a good job. So if it figures out that the repair is correct, and it could be the repair that was needed, then it passed the result to the static analyzer and LLM1 to validate the result. If it thinks the result is not correct, then it provides a feedback to LLM2 that telling LLM2 to retry, and I think it's incorrect because of this. And the hope is that the feedback can improve the accuracy of the second LLM. And this loop goes on until we have a contract that's fully fixed, or we have, or there's a scenario that the system was not able to generate proper repair. And the beauty about this is that it doesn't generate any false negatives. So if it tells you that the repair is correct, it's definitely correct. If it cannot generate the repair, then it tells you that the repair is not doable. So as a result, when you put the input in the third example that I show, it will actually completely modify the smart contract and generate a contract free of gas vulnerabilities. So at the time that I was making these slides, the work actually was in progress, but luckily we finished the work. The accuracy is pretty solid, considering that we're using AI. For the first LLM that we use fuzzers, the first LLM is capable of writing test cases for 95% of the cases. And even if it's not able to find proper test cases, it's fine, because the second and third LLM would catch any problem that's there. The second LLM, this one, in the first try, we were able to get an accuracy of 85%. But then when we use the feedback of the third LLM, after the first feedback, we were able to get an accuracy of 90%. And after the second feedback, we were able to increase that accuracy to actually 96%. So this was an estimate in the slide, but the actual value is 96%, meaning that we were actually able to increase the accuracy by 11% by using the feedback loop. So this process is fully automatic from detection all the way to repair. It takes about 20 minutes per loop to perform this operation, the operation that traditionally used to take about days or weeks to manually get fixed. And so our hope is to improve our design to be able to cover more vulnerabilities like gas-based vulnerabilities. And we've seen that LLMs have been showing promising results for us. Thank you so much for listening. If there are any questions, I'll be outside for about an hour so we can discuss more. Thank you.